Unit 3, Topic 4, we're going to be talking about potentiometric titrations as well as voltammetry. So up until this point, we have only used a 2-electrode system. Now we're going to introduce a 3-electrode system. We have 3 primary instrumental methods that we can use in the laboratory in order to measure the electric response of chemical compounds. There's amperometry, and that measures electrical current with a fixed applied voltage. Usually you see that like an electrolysis reaction. You have voltammetry, which measures current while the voltage between the electrodes is varied, and you have what's called a potentiostat in order to do that. That's basically like a fan control or a dimmer switch on your wall for a light. That's a potentiostat. And then we have a special case voltammetry, and that uses what's called a dropping mercury electrode. So rather than having your electrode get coated with analyte after reactions occur, you have a liquid mercury drop that forms, and we can measure, as long as that drop is attached to the electrode itself, you can measure the potential. Now, when that drop gets heavy and drops off, then we have a renewing surface. We have a new drop that forms. So it's a pretty cool technique, but we're going to focus on voltammetry, more the general version. In voltammetry, as I mentioned, we have a 3-electrode system. So electrode number 1, all the way over here on the right in the red rectangle, this is what's called the working electrode. The working electrode in previous weeks would have been called the indicator electrode. So this is where we're going to be measuring the potential that is occurring in our chemical solutions. And we measure that against these standard electrodes. So you see that part hasn't changed. The standard electrode often is going to be something like the saturated calomel electrode. It could be your silver electrode. It could be your standard hydrogen electrode, but it's going to be a standard electrode nonetheless. Now, the standard electrode, 99% of the time, is going to be hooked up to the anode. The working electrode is going to be, most of the time again, the cathode. Now, if you have a problem that says the saturated calomel electrode is hooked up to the negative side of a potentiometer and the working electrode is hooked up to the positive, again, it's telling you which is the anode and which is the cathode. So you have to remember those notation shortcuts, for lack of a better word. So we have our working electrode, that is the cathode. We have our standard electrode, that is the anode. So what's this over here, this other electrode? Well, we call this the counter electrode. Sometimes we call this the auxiliary, I can't spell auxiliary, one L. Sometimes we call this the auxiliary electrode. It's either counter or auxiliary. It's not the counter auxiliary, okay? It's one or the other. And that is where we're going to be measuring the amps. That's also where the opposite reaction occurs. Remember, we can't have oxidation without reduction, and we can't have reduction without oxidation. So if our working electrode is attached to the positive side, it's only really measuring reduction. So if we're going to be having reduction, we must have oxidation as well. And so that's what's happening at the counter or the auxiliary electrode. Now, when we have one of these systems hooked up to a potentiostat and we can read its readout, and way back in the day, we had these plotters that would do this, and it was fun to watch. But now I'm sure they just spit it out in a computer. Anyway, you can see how the curve, the initial curve here, starts to look like a titration curve, and then it tails off. Well, going from left to right, the way that this potential is down on the x-axis and current is on the y-axis, this is called an oxidative scan. It's measuring the oxidation of whatever we're measuring. And then we can use that potentiostat, like the dimmer switch on a light, and we can dial the potential back, and then we can watch the reduction. I can't even draw on the line. I am not an artist. So then we can watch the reduction. So we have our oxidative scan, we have our reduction scan. We can turn the potential up and we can turn it down, and we can watch how the chemicals respond. Now, like other titrations, we can also have indicators. Now, when you're going to pick an indicator, you want to pick one that has an E0 value approximately equal to or very close to the E naught found at the equivalence volume of your titration species. Now, we would use a potentiometric titration if the potential difference between the titrant and the titrand is less than 0.2 volts. So we need that readout. We need that descriptive graph. If the potential difference is more than 0.2, and really I prefer the basement as 0.4 for your potential difference, then we would use something like a colorimetric indicator. But with very little voltage difference between your titrant and your titrand, you would actually use a potentiometric titration. Now, we have iodine that's often used in potentiometric titrations, and it's considered a special case. I2 iodine. Ooh, I can't write with that. So I2 is a mild oxidizing agent. So that means it reduces, reasonably. And then we have our iodide. Iodide is a mild reducing agent. Now I feel like I said that backwards. So I2 is a mild oxidizing agent. It gets reduced. And iodide is a reducing agent. It oxidizes. Now, iodine is great because it can be used for so many different things. Iodine can be used to determine vitamin C in a number of things. It reacts with ascorbic acid. It can be used to determine starch in grains. And a very common reaction, at least for general chemistry students, is to take an iodine and react it with sodium thiosulfate. So sodium thiosulfate can be found as a chlorine reducer. If I'm not mistaken, it's a chlorine reducer for aquariums. So you can actually find these things just at your basic everything store like a Walmart or a Target. But iodine reacts with a number of different analytes. And one of the cool things about iodine is iodine in its diatomic form plus an iodide will form I3 minus. Now this I3 minus is also reactive. So we have three different reactive species. In iodometric titration, where we are reacting this I3 negative species, we have specific reactions for that. Now, I'm not going to belabor the point, and I'm not really going to go into it real hard. If you end up using this in the lab, I'm happy to go into this further, but this is it's used in the lab really, but it's not necessarily used much in industry, at least not in the industry that I've been a part of. That doesn't mean it's not used. It just wasn't used when I was in the industry. So again, I'm not going to belabor this because I think it's more important that we spend time with the actual titrations. Titrations seem to be a sticking point, at least in this particular class. So we're going to go over these machinations slowly. Now, like other titrations, we have three distinct ways to calculate this. We have before the equivalence point, at the equivalence point, and after the equivalence point. So obviously we must need to know where that equivalence point is. And it's pretty easy to calculate when what we're calculating is the equivalence volume, the VE. So before the equivalence point and after the equivalence point, we're going to be using a Nernstian equation where the cathode is dependent on the excess reagent. And then we're going to subtract from that the voltage of this standard electrode. I'll show you how that works. But at the equivalence point, this is the part I need to really emphasize. We're not using a Nernstian equation. So the E of the cell at the equivalence point is going to be equal to N1 E1 plus N2 E2 all over N1 plus N2. What in the world does that mean? Well, we're just going to take our half reactions of our titration and we're going to say one of them is 1 and the other one is 2. It doesn't matter which one you use, we're adding. So it doesn't really matter as long as you keep your 1s and your 2s together. And I'll show you what that means. But that's the cathode part, and then the anode part is then, of course, your standard electrode potential, whatever your standard is. For some reason, I want to leave that off. So if I do leave that off in my problem solving, please call me out, because it's important that that part is kept as well. So we're going to start with this example, this 16.2. So 16.2. So before we can really calculate this, we need to know what figure 16-2 is. So I went and grabbed that, and here we go. And this gives us a lot more information because we have concentrations and volumes and stuff too. So starting from the beginning, let's write a balanced titration reaction. We know we are starting with Fe2 and cerium 4. So I don't know what's going to happen with iron and cerium. So I'm going to go to the classroom, and I'm going to go to the standard reduction potential table, and I'm going to see what I can find. Now for cerium, I'm looking for cerium 4. Cerium 4 will only be reduced. So here we go. 1 electron and cerium 3. 1 electron, cerium 3. So we need to know what kind of conditions we have, because if you'll notice, there are 5 different potentials given. So over here, I'm just going to have a look, and it specifically says down here at the bottom that we are in 1 molar HClO4. So I come back over here and look for perchloric acid, and I have a potential of 1.70. That is my standard reduction potential of this half reaction. So if the cerium is going to be reduced, that means the iron is going to be oxidized. So we're going to make iron 3 here. Iron 3 also will give off 1 electron, so that's convenient. We have a 1-to-1 relationship. I just want to grab that iron. I just want to grab that potential. So iron with perchloric acid is 0.767. So our A, balanced titration reaction, is going to have iron 3 and cerium 3 on the product side. So the two half reactions for the indicator electrode. Now, we already wrote half reactions, so why would it ask us to do that again? Well, the reason is because at the indicator electrode, or at the working electrode, we're only going to be having reduction. So I'm going to write this as reduction because we're going to need that in order to come up with our Q ratio for our Nernst equation here in just a moment. So Fe2+. Then for C, we're asked to write those two Nernst equations for the cell voltage. So E, when the cerium is in abundance, is going to be equal to, so we have the cathode minus the anode. The anode here, it says down at the bottom, is the saturated it says it right here as well, is the saturated calomel electrode. So we know the voltage of that. But we need to start, when we have an excess of cerium, we're going to start with the standard reduction potential for that analyte, and then subtract the product of 0.05916, our constant, divided by N. Remember, N is the number of electrons that are transferred. We have 1 here. That makes it nice and tidy. Then we have the log of the Q value. This is where the reduction comes into place. So the product of the reduction is cerium 3, and the reactant of the reduction is cerium 4. So we need those concentrations in order to calculate this. I'm going to move this over just briefly. Now, from there, we're going to subtract our saturated calomel electrode, 0.241 volts. So that is the equation we use if we have an excess of cerium. If we have an excess of iron, the equation is found similarly, starting with this standard reduction potential, minus 0.05916 over N times the log log of the Q value of the reduction. So we take the concentration of the iron divided by the concentration of the iron 3, all as the E of the cathode, minus 0.241 volts. So that's the reaction that's the equation we're going to use if iron is in excess. So now we're going to calculate the E at the following volumes of cerium, except I'm going to trim this down a little bit, and I'm just going to pick a before, at, and after. And I have a feeling I know what that VE is, but we're going to calculate it anyway. So for D, whenever you're asked to calculate the potential, you need to know where you are in the titration. So the VE is going to be equal to, we're going to start with the initial volume, which is found in this figure. So we have an initial volume of 100 milliliters of iron 2, and that iron 2 has a concentration of 0.0500 moles per liter. We know from the balanced chemical equation we have 1 mole of iron reacting with 1 mole of cerium, and we know that our cerium concentration given right here is 0.1 molar. So that's moles of cerium per liter of cerium. So I run that equation, or I run those calculations, and I get that the equivalence volume is exactly 50 milliliters. So in order to find the potential at 49 milliliters of cerium added, I have an excess of iron. So I need to find out how much my excess iron is. I'm going to erase these 2 bits right here because I'm actually going to use this space. So first I'm going to calculate how many moles of iron we started with. So we started with 100 milliliters, and we have a concentration of 0.05 per liter. So that means that we have 5 times 10 to the negative third moles of iron 2 that we start with. Now I need to calculate how many moles of cerium have been added at this point. So we have added 49 milliliters, and those 49 milliliters have a concentration of 0.1 moles per liter. So I have added 4.9 times 10 to the negative third moles of cerium. Well, just like in our other equilibrium titrations, I have an amount that I've started with, and I'm ignoring significant figures for these examples right now. So this is how many moles of iron I started with, and then I added 4.9 times 10 to the negative 3 moles of this. That means I'm going to shift towards the production of my products. So I'm taking 4.9 times 10 to the negative 3 moles of this away, and I have so let's write it up here. I have the excess Fe2 plus is going to be 1 times 10 to the negative 4 moles of Fe2. That's my excess. So how much Fe3 do I have? Well, I have a molar amount equivalent to what I've added, what I've taken away from the Fe2, but what I've added in the cerium. So I have 4.9 times 10 to the negative 3 moles of Fe3. So why do I care about the iron and not the cerium? Well, the answer to that question would be because we have an excess of the Fe2. Because once we've added the cerium 4 at 49 milliliters, I've used it, and I've used it to convert it into Fe3. Now, just like with the Henderson-Hasselbalch equation, you can use moles in this equation. It might be best practice to have you convert that into molarity. I use moles. So the potential, we're going to use the iron equation at 49 milliliters of cerium added is going to be equal to 0.767 minus 0.5916 times the log of the ratio of iron 2 to iron 3. So all of that, and then we subtract the saturated calomel electrode. Now, when I calculate that, I get that the potential at 49 milliliters of cerium added is 0.626 volts. So now, what about after 50 milliliters of cerium added? Well, if I'm at 50 milliliters of cerium added, I am at the equivalence point. So when we are at the equivalence point, let's go with green. So at 50 milliliters, we are at VE. We need to use the equation that the E of the cell is going to be equal to N1 E1 plus N2 E2 over the sum of N1 and N2. Well, we have to decide which one's going to be 1 and which one's going to be 2. I'm going to call this one 1 and this one 2, purely for the sake of I wrote the cerium first. It doesn't matter which you assign. So N1 is 1. There's 1 electron traded. And the standard reduction potential of the cerium equation is 1.70. Now I'm going to add to that the product of N2, there is 1 electron traded, times the standard reduction potential of the iron, 0.767. And then that sum will be divided by N1 plus N2. So working this algebra out very quickly, and I nearly did it again. So we need to subtract, this is the cathode. Remember, the E of the cell is always going to be the cathode minus the anode, minus 0.241. So the E of the cell at 50 milliliters, I get 0.99, I guess I'd call that 3 volts. And looking back, because of these significant figures, I'd probably just call that 0.99. I don't think I'd count you off if you had 0.993, but 0.99 is appropriate. So that is at the equivalence volume. Now, after the equivalence volume, we're going to have an abundance or an excess of our other reagent. So after the equivalence volume, at 51.0 milliliters of cerium added, we have more moles of cerium than we do iron 2. So we need to calculate how many moles of each we have. So the moles of cerium will be found by taking 0.0510 liters and multiplying it by the concentration, which was 0.100 moles per liter. So I get 5.1 times 10 to the negative third moles of cerium-4. That's what we've added. Now, what we've started with hasn't changed, though. So we started with, let me drag this back down again, we started with 100 milliliters of a 0.05 molar iron. So I knew that was going to happen, and I did it anyway. There we are. So our moles of iron, we're starting with 2, not 3. Our moles of iron are going to be equal to 0.100 liters times the concentration So we start with 5 times 10 to the negative third moles of iron 2. Now, as before, and with all of our other titrations and such, we have the amount that we've started with, so 5 times 10 to the negative third moles, and now we've added 5.1 times 10 to the negative third moles. So that means all of these moles have been consumed, and we've pushed them over to here because it's a 1-to-1 arrangement. So now we have 1 times 10 to the negative 4 moles of cerium-4 because we've used the 5, I put 5.1. We've used the 5 times 10 to the negative third moles of cerium-4 to react with the iron 2, and we have created cerium-3. So we have an excess of our cerium 4. So at 51 milliliters, in order to find the potential at this particular place, we need to use the cerium equation. So I will start, let's see, the E of the cell is going to be equal to 1.70 minus 0.05916 times the log log of the Q value. Again, the Q value is based on the reduction reaction because that's what's happening at that working electrode. So the cerium 3, we have 5 times 10 to the negative 3 moles of that. And cerium 4, we have 1 times 10 to the negative 4 moles of that. And that represents the potential of the cathode. Then we're going to take away 0.241, or the potential of the anode. So at 51 milliliters of cerium added, you should have an E of the cell, or a potential for the cell at this point, of 1.36.